Our first speaker is from Washington University. It is Michaela Schwaiger Haber. I think I did okay with that. So take it away. You're muted.
Sorry about that.
Yeah.
Then I had to just, okay. There we go. Now you can hear and see.
Yep.
Okay, sorry. Yeah, so I'm Michaela Schwaiger Haber. I'm a postdoc in Gary Petty's lab at Washington University in St. Louis, and I will briefly talk about how we can use a triple quadrupole mass spectrometer for untargeted metabolomics. And to give you some background, the field of metabolomics has increased the sample size over the last years pretty drastically, and triple quads are also already really established in clinical settings. It also has further advantages in that we can use optimal voltages, for example, the fragmentor or RF voltage for each metabolite, and we can easily choose the polarity, positive or negative mode for each metabolite, the one that works better. And we can acquire those data in one run. The big disadvantage is that we need to know prior to acquiring data what we actually want to measure. And that might sound a little bit counterintuitive if we talk about untargeted metabolomics. And as we've heard over the last few days, identification is still a big challenge. So how are we going to do that? And it would feel awkward to explain you how a triple quad works. Most of you know, and with Wikio still around, I do not want to do that. But just as a reminder, if we use a triple quad, we need to know precursor and product M/Cs and corresponding collision energies in order to be able to acquire data. So we were wondering, can we actually do this optimization that is usually done on the triple quad itself on a high-res instrument, such as an Orbitrap or a QTOF? And what we did is we started with standards, metabolite standards, and acquired MS2 data with a targeted list on 10 different collision energies on an Orbitrap system. And we then used the Python script to extract the best fragments. So we didn't know what the fragments were beforehand, and also the optimal collision energy at the Orbitrap system that yielded the highest intensity. We could then, based on the data that we obtained from the standard optimization on the triple quad itself, calculate or predict the collision energy that we need for a specific triple quad based on the collision energy that we obtained on the high-res instrument. And with those values that we predicted, we generated two different methods for the triple quad, one with our predicted values and one with the ones that we obtained from the standard optimization on the triple quad. And we found that the peak areas are almost identical. And initially, I used about 500 metabolite standards for that, but I didn't want to tell people that they need to run that high number of standards on both instruments. And I found that we can even just use 10 compounds of diverse metabolite classes and get a really good correlation. For the RF voltage or fragmentor voltage, we can really just use the calibrated RF on the instrument, or for the Agilent, it's the fragmentor voltage that is just dependent on the precursor M/C, and that doesn't need to be optimized. And that works really well. So to give you an overview over the final workflow, so what you can now do is you can take a pooled reference sample or several, acquire MS1 data on a high-res instrument, and then do peak detection. You get your features, you then filter them down to just get unique metabolites. Independent of whether you know what they are or not, you can generate an inclusion list, acquire MS2 spectra at different collision energies, and then from that via the conversion, generate a triple quad method with MRMs, and acquire all your research samples just on a triple quad and save time on the more expensive high-res instruments. And with that, I would like to thank everyone in the Petty Lab, especially Miriam and Ethan, with whom I've worked on this project, all of the collaborators and the NIH for funding. And if in case anybody's interested, I'm happy to take questions in the chat. And we published this last year in ACS Measurement Science. Thank you.